Hello engineers, today's discussion is on earthing basics for substation design. The earthing is a very critical part of substation designing. It is also termed as grounding. It is one of the most critical aspects of substation engineering because it directly governs the personal safety, equipment protection, and system stability. So these system stability and equipment protection and personal safety depends on this earthing design of earthing system. And the ultimate goal earthing design is to provide a low impedance path. It must provide a low impedance path for fault currents and during also fault that means low impedance for the fault currents. Fault currents due to the different types of faults are there. And line to line or line to earth, or it may be a lightning surges, heavy lightning during the period of heavy lightning, huge amount of current is dissipated. It must be safely dissipated into the ground while keeping the surface voltage gradients with the tolerable limit. When the fault current is to pass, the safe voltage gradient should be maintained. The earthing basics for the substation design. The safety parameters for design are few things. First is the step potential. The step voltage, the voltage difference between the person speed 1 meter apart during a fault. What should the step potential? It should be within the minimum value, limiting value. Similarly, torch potential, what is the torch potential? The voltage between an earth metallic structure and the ground, where the person is standing. Touching the ground, it touching the structure, metallic structure. So the potential difference when the person is standing normally 1 meter away. Similarly, on mesh potential, the maximum touch voltage generated within the single mesh of the earth grid, typically highest at the corner of the meshes, where curvature is maximum. The earth potential rise, it is another factor, parameter, and the maximum electrical potential, the substation grid reaches relative to the remote earth. You can calculate the GPR or EPR, it's also called. That is IF into RG, where the IF is the fault current and RG is the grid resistance. So what are the objectives, earthing basics for substation design? What are the objectives for the while designing a substation? The objective is the earthing system. The earthing system must be safely dissipate the fault current into earth. It will maintain the earth potential rise within the limit. Also, step potential and touch potential should be within safe values. It must provide the low impedance to the return path to the fault current, ensure proper operation of the protection systems. Proper operation should be there. Relays and cities will be operated properly. What are the key concepts of earthing for substation design? First, your earth resistance, RG. The resistance between the earth grid and the remote earth for typical small substation is generally less than or equal to 1 ohm, and for large substation is less than or equal to 0.5 ohm. The earth potential rise EPR is equal to IF into RG, where I is the fault current in kiloampere and RG the earth grid resistance. Here the fault current, if the fault current is higher, then it leads to higher value of EPR, which is more dangerous. So the EPR value should be minimum. Another factor is your step potential, and torque potential should be within safe limit. For typical value of, we have taken the typical value of tolerance limits for step potential and torque potential. It is for 50 kg to 70 kg person. The fault duration 0.5 second is around 100 to 200 volt ampere. Similarly, torque voltage, the equipment body, it is the voltage between the equipment body and the ground, and typical tolerance limits for 50 to 70 kg person. The fault duration 0.5 second and roughly 50 to 70 volt. Both steps tolerable torque potential and step potential can be calculated as per the IEEE 80 and IEC International Standard, European Standard 61936. So the standards we follow during the design of the earthing system, IEEE 80 and IS 3043 Indian Standard and IEC 61936. So what are the earthing system components? The earthing system components are the earth grid, mat, buried horizontal conductors with horizontal conductors, and vertical conductors. Vertical conductors are the electrodes. Earth conductors connect equipment to the grid. Vertical earth electrode, and these are the horizontal conductors forming a mesh. At the cross section of the mesh, electrodes are installed. The mesh is typically 0.5 to 1.0 meter in depth below the ground level. In vertical earth electrode, GI pipes or copper rods are used to reduce the resistance. It is also 2 to 3 meters. Earth conductors connect the equipment to the grid. The earth conductors may be flat or GI wire, earth wire. Then earth feeds gives or provides the maintenance access to the earthing system. And surface layer, during the earthing system, surface layer should be a rock, should be a layer of rock or gravel, which increases the surface resistance, which increases the surface resistance, which reduces the shock risk. Then what are the desired design inputs? What is your soil resistivity? Soil resistivity can be found out by using UNR 4P method. It will be fault current in kiloampere. For input data, we can calculate this fault current. Fault duration typically 1 second. Substation area layout, grid geometry, and equipment locations. All these things are required for designing the earthing system or substation design. Soil resistivity varies during the season. For clay, it varies from 20 to 100 ohm meter. For sand, it becomes 100 to 1000 ohm meter, and rocky soil it becomes greater than 1000 ohm meter. High resistivity soil require electrodes required. The regular electrodes, vertical electrodes are inserted at the cross section of the cross section points of the mesh. These are required to reduce the earth resistivity to a lower value. So for high resistivity soil require the earth electrodes only. Then another thing is your basic design steps. What are the design steps during the first step is your calculate the fault current. Calculate the fault current from the short circuit study. From circuit study, you can find out the fault current. Similarly, these things will be worked out in higher classes. These are the preliminary basics. When I will give the training in depth, then we will calculate everything. Select grid area, copper pool substation, and 1 meter outside fence. Then conductor sizing. The thermal criterion is A is equal to conductor sizing is I into root T by K. I is the fault current, and A is the cross sectional area in mm square, and kiloampere fault current in kiloampere. K is the material constant. Typically, conductor size are G for Gi is to be 50 into 6 or 75 into 10. Similarly, for copper, it is 70 to 120 meter mm square. In step 4, the grid layout. Mesh spacing should be 3 meter to 7 meter. Smaller spacing is more safer but costlier. Smaller spacing is more safer but costlier. So we'll add vertical electrodes where the earth resistance is high. At grid intersections, at grid mesh intersection, grid intersections, we take the vertical rod, valid vertical electrodes, 2 to 3 meter length. Step 6, calculate the grid resistance, rho G, Rg is equal to rho by 4L, where the rho is the soil resistivity and L is the total buried conductor length. Total buried conductor length of the mesh and as well as the length of the vertical electrodes. In step 7, check safety criterion. Torch voltage should be less than the permissible limit. Step voltage also less than the permissible limit as per IS IEEE 80 equations. Then now we will know what are different types of earthing for the substation. That is, first is your equipment earthing, transformer body, circuit breaker, structure, your neutral earthing for transformer, solid resistance, reactance, grounding, lightning earthing, lightning earthing, lightning arresters. Lightning arresters are the lightning earthing, separate, not bonded. Separate but bonded. Lightning arrester should be separate, bonded to earth. Fence, earthing, fence should be, the substation fencing should be earthed. Prevent transfer potential. Fencing must any transfer potential will be broken there. At fence, it will properly earthed. So what are the practical design guidelines for designing earthing system? GI is taken for economy and copper for critical systems. Provide minimum 2 earth connections for equipment. All metallic parts must be bonded. Avoid long isolated conductors. Ensure grid continuity, no open joints. Use exothermic welding or proper clamping. What are the common mistakes we encounter? Ignoring soil resistivity variations, we always, during the calculation, we take the soil resistivity variations, ignore the variations, take the undersized conductor, earthing conductor, poor bonding of structures, no gravel layer, improper electrode placement, not checking the step and toss voltages. These are the common mistakes we commit during the earthing design. So today, this much only. We'll discuss more about the substation design in coming classes. Thank you.